It's 4 p.m. in Japan and 9 o'clock in Italy, Europe. So let's start this seminar. So good evening and good morning, everyone. I'd like to open the webinar now. I'm Waseda from Kansai University, and I'm one of the organizers of this webinar. I'm also in charge of today's moderator. So first, I would like to express my gratitude to you for joining this webinar, Frontiers of Concrete Technologies. This is now our 5th webinar, where today's theme is Advances on Life Cycle Bridge Engineering. So today, we invite 2 leading researchers regarding this topic. Professor Fabio Biondini from Italy and Professor Mitsuyoshi Akiyama from Japan. They will give us advanced information on life cycle bridge engineering. 30-minute presentations are scheduled from each researcher. So this is the schedule of today's webinar. First of all, I'd like to introduce the Japan Society of Civil Engineers, JSCE, and the Concrete Committee, since this webinar is organized by JSCE. Then, after that, Professor Biondini and Professor Akiyama give us their research presentation, respectively. We also schedule short Q&A after each presentation. After their presentations, we have the panel discussion with them. So before moving on to the first content, let me announce some notes. During the presentations, you might have some comments or questions. At that time, please use the Q&A box as shown here. Please note that write your name, affiliation, and your comment and or questions. Some of the questions or comments will be selected to answer from invited researchers and to deepen discussion on them in the panel discussion, depending on the situation. So I'd like you to submit your questions or comment positively. But due to the time limitation, we cannot answer to your all questions. Thank you for your understanding. So today, we plan to broadcast this webinar on YouTube live streaming, but now some troubles occur, then it doesn't working on live streaming, but maybe you can see this webinar via Zoom. So this webinar will be broadcasted on YouTube after webinar. So we will send you the address after finishing the webinar. So if you check the webinar more deeply, please access the YouTube. So let me introduce the JSCE and the Concrete Committee now. JSCE has a long history of more than 100 years and is also one of the biggest society in Japan. The current members are about 40,000. JSCE is now focusing on international activities and promoting them all over the world via web page and SNS. And JSCE has several research committees. One of them is the Concrete Committee, which we are belonging to. This webinar is one of the activities of this committee. The most important activity of the Concrete Committee is to publish standard specification for concrete structures. The latest version has been just published last month. Those specifications will be translated into English in the future. Now you can download the previous specification of the English version freely from the web page of Concrete Committee. The Concrete Committee also focuses on international activities. We have issued a newsletter every 3 months to inform the latest activities. Moreover, we have an international seminar every year with many Asian countries. This year, we will have a face-to-face seminar in Thailand after a few years because the situation of COVID-19 has calmed down a bit. Of course, this webinar is one of the international activities of the Concrete Committee as well. As I told you before, today's webinar is the 5th webinar. That is, we had 4 times of webinar up now. So you can watch the past webinars on YouTube. Please search JSCE or Frontiers of Concrete Technology if you're interested in. Yes, so let's move on to the main portion. Now, I would like to invite Professor Fabio Biondini as our first presenter. Prior to his lecture, I would like to introduce about Professor Biondini briefly. He is a professor of structural engineering and chair of the civil engineering degree program at Politecnico di Milano. His research interests cover several topics, such as life cycle risk, reliability, robustness, redundancy, and resilience of deteriorating structures and infrastructure systems. He is the chair of SIE Technical Consult on life cycle performance, safety, reliability, and risk of structure systems. He is also co-founding executive board member of IARCHE, executive committee member of IAVMAS. He serves in leadership roles several international scientific and technical committee as well. He is associated editor and editor board member of several international journals such as Structure and Infrastructure Engineering, Structure, Engineering Structures, and Journal of Structural Engineering. He has won the several awards from up to now. So today, he delivers a lecture entitled Life Cycle Bridge Engineering, Risk-Based Prioritization and Experimental Validation. So, Professor Biondini, please share your slide and start your presentation when you are ready.
Well, hello everyone. Good afternoon in Japan. Could you see my slide?
Yes.
Okay, so thank you very much, Professor Waseda, for your kind introduction. I'm really happy and honored to join you and Professor Mitsuyoshi Akiyama and other distinguished colleagues for this webinar. And also I wish to thank very much the Japan Society of Civil Engineers for the invitation to deliver a presentation related to recent advances on life cycle bridge engineering. Life cycle maintenance and management of aging bridges and infrastructure systems, we know is a high priority, and public authorities and managing bodies need risk-based life cycle-oriented criteria, methodologies, and tools to inform the decision-making process for a rational allocation of available resources and for efficient prioritization of bridge maintenance and repair intervention. On the other hand, the life cycle methodologies need to be supported by data and extensively validated based on inspection of existing structure and experimental test. And this is particularly in view of the relevant uncertainties associated with aging and deterioration processes. So my presentation will focus on these topics and is organized into two parts devoted each one to a different research project. And in the first part, I will introduce a methodology for early bridge assessment and risk-based prioritization at infrastructure scale, while in the second part, I would like to present the results of an ongoing experimental campaign on existing bridges and also the exploitation of the results of this campaign for validation of life cycle-oriented computational models. The increasing age of bridge stocks require management policies able to maintain the required levels of structural safety and functionality by using the limited budget that is available for agencies and authorities. Bridge management systems are frequently used for this purpose. They allow for condition assessment of individual bridges during their life cycle and provide at the same time efficiency and functionality information when allocating resources and establishing management policies in a bridge network. So in this way, decision-making can select optimal solutions and evaluate and compare alternatives for bridges in the network within risk-based lifecycle management frameworks for bridge prioritization. So these frameworks typically require to collect data on existing structure from inspection, surveys, diagnostics, and monitoring. And this activity can be very costly and available resources may be too limited. So as an example, according to the most recent report card for America's infrastructure issued by the American Society of Civil Engineers, there are over 230,000 bridges out of the about 600,000 bridges in the United States that need significant repair. And also the number of bridges, as you can see here, that are slipping from good to fair condition is increasing annually. That is, the rate of deterioration is exceeding the rate of repair, rehabilitation, and replacement. This management problem can be very difficult to afford, even at smaller scales. Italy, for example, shares several similarities with US regarding the stock of existing bridges, even though the total number of bridges is smaller. A strong effort is currently ongoing to establish inventories at both national and local level. And as an example, in Lombardy, that is an administrative region in northern Italy, constituting more than approximately 1/6 of Italy's population. In this region, there are approximately 10,000 road bridges, which data are being collected in a dedicated road information system. However, as already mentioned, the detailed inspection and evaluation activities needed to inform bridge management may require time and cost that can be extremely high and not always affordable. And this is especially when these activities concern entire regional or national infrastructure system. It is therefore essential to exploit information already available, properly organized and stored in a systematic form to carry out a preliminary assessment of the intervention priorities, mainly on a documentary basis. In this way, the limited resources available can be more effectively allocated for targeted inspection and maintenance activities, for example, to gather new information for safety assessment according to the design standards and codes, and in this way refine priorities. Risk assessment procedures used to this purpose should account for the main risk factors that are related to bridge vulnerability and hazard, as well as exposure associated with functional loss or interruption of the network due to maintenance or unusability of individual bridges. To face these needs, a research agreement between Regione Lombardia, the Lombardy Regional Administration, and Politecnico di Milano has been established to define criteria and guidelines for maintenance and management of the regional roadway infrastructure. A risk-based methodology has been developed and applied to a sample of about 400 bridges belonging to the main routes of the regional road infrastructure. And in addition, to complement information from risk assessment, a variety of monitoring systems, including global navigation satellite systems, have been designed and implemented on a group of bridges selected as pilot case studies and are currently collecting data. Now, the key factors that determine the bridge safety level have been identified and organized in a bridge form to collect data and develop a bridge inventory. And about 70% of the initial sample have been filled by technicians of the provincial administrations with the support of dedicated staff of Politecnico di Milano. On the basis of the data information gathered, bridges have been also grouped into 6 clusters as homogeneous as possible, taking into account different bridge features such as material, structural type, structural scheme, and main geometrical dimensions. Here you can see the distribution by material and structural scheme, and the most represented are reinforced concrete and prestressed concrete bridges with simply supported deck. In the proposed approach, the risk level and choice of bridges to be subjected to prioritization derive from a documentary analysis of the main risk factors affecting individual structures, and including bridge intrinsic vulnerability, condition state, traffic loading, and other site-dependent hazards. And also the road infrastructure in terms of impact of bridge closure on the network, functionality and efficiency is taken into account, particularly with reference to the consequences for infrastructure users. So vulnerability and hazard are addressed at the bridge level to establish technical priorities, while exposure is covered at the road infrastructure level in terms of functional priorities. Technical and functional priority indicators are then aggregated to establish a risk-based rating system for bridge maintenance prioritization. Now, based on the information stored in the bridge form, the analysis at the bridge level is conducted considering vulnerability and hazard key factors listed into this table. And particularly, vulnerability factors include both structural features and for river bridges that are related to the riverbed, to some details of the structure relevant for the hydraulic vulnerability assessment. The definition of the intervention priority is based on a discrete ordinal classification, and considering the documentary and incomplete nature of the information processed, only 4 classes of attention are considered from low to high. The risk factors are grouped into primary and secondary variables according to their importance and processing sequence, and the evaluation algorithm for the attention class is based on logical and algebraic operators that are processing the primary variables associated with bridge vulnerability. For better prioritization, intra-class subdivision are also introduced. This will allow for a more detailed classification, and it is determined on the basis of the secondary variables related to both bridge vulnerability and hazards. The combination of the 2-level evaluation identifies in this way a priority class with 16 levels. Of course, into this process, structural deterioration is one of the main factors considered. It is affecting structural safety over time, and also due to the interaction with fatigue, and it has to be taken into account as the primary factor. For bridges, there are concomitant aspects that may also favor the evolution of degradation, and these include incorrect rainwater conveyance, poor quality of the materials, lack of care in structural detailing, and other important criticalities that may arise, for example, from malfunctioning of joint devices, which may involve dynamic overstresses and consequent cyclic degradation of the adjacent structural parts, and support devices that they can give rise to abnormal stress states and damage propagation. Moreover, different materials may have different durability and sensitivity to degradation phenomena, and the type of structural scheme also influences the level of redundancy and robustness of the system, leading in some cases to situations of potential fragility. This is the case, for example, of pre-stressed concrete structure, characterized by a greater sensitivity to corrosion processes compared to reinforced concrete structures. And also of Gerber girders, for example, in which the support saddles often have surfaces with water dripping, deteriorated concrete, spalling of the concrete cover, and corrosion of the reinforcement. All these aspects must be taken into account into the risk classification. As an example, this is the distribution of the damage processes by type and levels in the investigated sample. As you can see, the most critical items with a percentage that is ranging from about 30% to over 40% are related to aging of materials and components, corrosion phenomena, and the damage of mechanical devices of supports and joints. So structural tension class is firstly defined considering the breach condition states in relation to both the level of damage and historical information concerning the year of construction and inspection activities. And this information has to be elaborated according to the type of materials based on available information and expert judgment. This matrix, for example, aggregates the information about type and level of damage to identify the structural class by damage with reference to the worst case scenario. Information related to damage is combined, as mentioned, with historical information related to breach age and time interval since the last inspection, taking into account also the type of material. This is based on these three aggregation matrices, each one associated with different time intervals since the last inspection. The matrices also identify, as you can see, 5 time intervals for the year of construction, and they are determined with reference to the dates of issue of Italian design codes that have introduced significant changes in the structural design of bridges in relation mainly to both traffic loads and seismic actions. Class levels associated to damage and historical information are finally combined, giving greater importance, of course, to damage class compared to class associated with historical data. And also bridges that are not categorized because of lack of information are immediately candidates for action aimed at gathering new information. So this is the final distribution of the structural tension class. These are quite big groups, and so this distribution is not yet very effective for bridge prioritization. So for a more detailed ordinal classification, intra-class subdivision should be also considered within each class. And the intra-class subdivision has been based on a structural vulnerability indicator in between 0 and 1 that have been associated with both the intrinsic bridge vulnerability based on variables such as materials, static scheme, number of spans, maximum span length, water conveyance system, and damage factor not yet processes at the first level. In fact, the importance of damage for bridge prioritization is related not only to damage intensity, but also to its extension. For example, considered as localized and isolated, localized and systematic, or diffused and spread over the structure. And also related to the potential evolution of damage in time, that is stable damage or progressive damage. Details about the aggregation matrix cannot be given here because of the time, but I would like to emphasize that for the intra-class subdivision, the vulnerability indicator lead to four intra-classes associated with results related to equiprobable vulnerability scenarios. On the left side, you see the distribution of the vulnerability indicator for the bridge sample compared on the right side with all the possible vulnerability scenarios that have been obtained through Monte Carlo permutation. So this distribution, as you can see, is well approximated by a triangular density function, which is used as a reference model to define the threshold as you can show in this diagram. So this will lead to obtain the distribution of structural tension class and structural vulnerability intra-class. Particularly, they are reported in the diagram bottom right. And you can see that situations of very low or very high vulnerability are less frequent than those of intermediate vulnerability, and the intermediate intra-classes are the most populated. And into this way, the risk prioritization is much more effective, and the 16 level work well for the investigated sample. Of course, we need to incorporate also information about hydraulic vulnerability and hazard, and this is done by following similar criteria to the one that I presented for structural vulnerability. Because of the time, I skip this part, and I want to show how combining structural vulnerability, hydraulic vulnerability for river bridges, and hazard factors, we can obtain technical priority classification, as you can see here, where you have a distribution of a bridge priority class for the entire investigated sample. In this chart, as you can see here, there are also 8 bridges that are identified and highlighted, and they are the pilot bridges that are monitored. You can see them into these pictures that are distributed over the regional network. The ranking provided is also organized by province, and this allowed the public authority rational allocation of the resources at the local level, considering the condition of individual bridges. However, this ranking developed at the level of individual bridges represent only the first module of a 2-level structure network risk assessment that is combining bridge technical priority informed by structural and hydraulic vulnerability and hazard, and infrastructure functional priority associated with road network exposure at regional scale. The consequences of the closure of a bridge have been taken into account, considering the impact on people in terms of delay of person per hour, and the impact on the traffic of goods, also in terms of time delay, or in this case, tons per hour. And different approaches have been considered. Local approach focusing on the possibility of detouring when a bridge is closed in the neighborhood of the bridge itself, or is investigating all the possible origin destination trips that become available, that are available after a bridge closure. And based on this, the impact at the network level can be evaluated. And of course, the impact at the network level is combined with the information associated with vulnerability and hazard. And in this way, we combine the technical priority to the so-called functional priority. And this table shows the priority matrix that realize this combination and allow an effective risk prioritization, also taking into account the impact at the infrastructure level. Of course, with reference to this priority matrix, we can define also risk classes, and 4 risk classes have been defined with 4 intervention policies associated with each class. For example, for risk class 1 and 2, which provide for more in-depth assessment, where necessary, the interventions are also applied in order to obtain a reclassification of the bridge into lower classes, for example, into class 3 or 4. So these higher risk classes are characterized by the same intervention policies and are distinguished only by the urgency in the implementation of these policies. Class 3 provides priority in planning of inspection, intervention, and implementation of the maintenance plan when compared to Class 4, for which it is only required to maintain regular inspection and control activities in compliance with current legislation. Here you can see the risk map that have been obtained applying these criteria. Of course, this kind of approach is necessary under very limited information and mainly for an early prioritization of inspection and maintenance. After priorities are established, however, accurate life cycle prediction models are necessary for a robust evaluation of the time variant performance indicators over the entire service life, taking into account the effect of maintenance and repair under uncertainties. So in this context, significant advances have been accomplished over the last 2 decades, and this is particularly to incorporate aging and deterioration models into probabilistic life cycle assessment frameworks and this is for a wide spectrum of damage mechanism. Just to make an example, if you consider the effect of corrosion in reinforced concrete bridges, we need to take into account for the steel mass loss of reinforcing steel bars, the reduction of steel ductility, and also the effect in terms of concrete degradation because of the splitting cracks that arise because of the formation of oxidation product and the consequent possible spalling of concrete cover. All these type of effects, damage effect, can be incorporated into assessment framework. Here you have highlighted how the steel mass loss can be taken into account, also considering the type of corrosion, uniform or pitting corrosion, the reduction of steel ultimate strain according to a proper interpolation of existing experimental data, and also models that allow for taking into account the degradation of concrete in terms of degradation of mechanical properties or spalling, as mentioned, of the concrete cover. All these damage models can be incorporated into finite element models developed with different levels of complexity. In this slide, as an example, there are 2 possible kind of modeling using beam finite elements, accounting for the material nonlinearity associated with concrete reinforcing steel and pre-stressing steel, and B-dimensional finite elements for plane stress analysis that are formulated in accordance with the modified compression field theory. These models have been used to simulate the response of corroded beams, as you can see into these slides. And we considered several experimental tests gathered from literature and different tests on beams under accelerated corrosion or natural corrosions for different level of steel mass loss. And on the right-hand side, you see the load versus displacement diagrams, and there is the comparison of experimental results in gray and numerical results in black. And as you can see, for the variety of case studies considered, the accuracy of the nonlinear analysis, this deterministic nonlinear analysis, is extremely high. So the variability of accurate deterministic model is also pointed out in a survey showing that advanced life cycle models are well established nowadays for some of the most detrimental damage processes, and this is including corrosion, and they are also rapidly becoming valuable for a wider spectrum of deterioration mechanisms. However, the deterioration models are also very sensitive to the change of the probabilistic parameters of the input random variable when they have to be incorporated in a probabilistic framework. And the robust validation and accurate calibration of these models are difficult tasks to be performed because of limited availability of data. And further efforts to gather new data from both inspection of existing structure and experimental tests are crucial for a successful implementation in practice of life cycle methods. And the Bridge 50 research project that I would like to briefly present here has been established to this purpose. This project includes a wide experimental campaign with full-scale load test on the structural members of a concrete viaduct dismantled after a lifetime of about 50 years. The project involves several partners, including Politecnico di Milano, Politecnico di Torino, and several public authorities and private companies. The main bridge span of the viaduct range from 16 to 24 meters, and the bridge deck is formed, as you can see, by a system of precast prestressed concrete beams, including 10 inner I-beams and 2 lateral box beams with a top cast in situ concrete slab. The deck girders are simply supported over each span, and we have reinforced concrete piers with tapered prestressed concrete pier caps. The preliminary activities conducted on site before the dismantling of the viaduct included visual inspections with the participation of several local and national public authorities and also private managing bodies. And the participants have been organized in inspection teams, and each group filled one or more inspection forms according to different standards established in Italy and other countries. The data gathered through this activity will be elaborated according to inspection model typically used in practice and compared with the outcomes of the experimental research in order to validate this inspection procedure both in qualitative and quantitative terms. The viaduct has been dismantled in 2019, and contextually a total of 29 deck beams and 2 pier caps have been collected from the deconstruction of 2 adjacent bridge spans by cutting the structural members and then moving these members by truck to a testing site managed by Politecnico di Torino, where the beams have been placed on New Jersey supporting members. Now, these structural members exhibit severe deterioration, mainly due to corrosion localized on both lateral box beams and particularly on the pier caps. The activities to be carried out in the testing site include photographic mapping of the structural elements, drone surveys, non-destructive diagnostic tests, and full-scale load tests, and that are also complemented by a large number of samples from the tested structural elements, I mean concrete cores and samples of reinforcing steel bars and pre-stressing steel wires, for laboratory mechanical and chemical physical tests to be performed either at Politecnico di Milano and Politecnico di Torino. Of course, the most important tests are the full-scale load tests that are performance on 3-point and 4-point loading scheme, as you can see here. This is the testing framework used with movable loading system that allow for load test with different shear span ratio in order to investigate both bending and shear failures. In this diagrams, you can see the results for 2 of the load tests conducted on 2 deck beams, and the results are in terms of applied load versus mid-span displacement. And as you can see, the results are very stable because we have a similar response for in this case for the 2 deck beams, and this consideration applies also to the other beams that have been tested recently. And a preliminary numerical investigation has been carried out on these beams, and in this slide you can see the numerical results of, in terms again of load versus displacement diagrams obtained for different span ratio using 2 different type of modeling based on beam elements or modified compression field theory. Of course, for a 3-point bending test, the results are practically the same because we have a pure bending failure, as the shear span ratio is decreasing, you can see that, of course, the shear effects are becoming more and more important. And since they are not taken into account in the beam modeling, the modified compression field theory give, of course, higher accuracy. But this is just to compare different type of modeling. Preliminary numerical investigation has been carried out also to compare numerical result with experimental results, and the tested beams have been modeled by taking the construction stages and the effect of a potential lack of the beam to slab connection also into account, because the failure of the beam under load testing was frequently obtained in consequence of the failure of the top slab. And so this has been taken into account also in the modeling of the beams. And these models, as mentioned before, have been based on two different type of approaches, using beam elements and modified compression field theory. Now, if you look at the load versus displacement diagram, you can see that the agreement of experimental and numerical results is for both types of modeling investigated is very high. Here is limited, the results are limited to those obtained with the modified compression field theory, but for the preliminary test also the modeling with beam elements provide very good results. The comparison is excellent also for other aspects that characterize the structural response. Here you can see as an example the crack pattern resulting from the load test that I would like to mention that has been also incorporated in digital model. This is another important part within these projects, and the comparison with the numerical result that you can see at the bottom part is also quite good. Currently, we are in the process to complete the experimental campaign planned on all structural elements that are stored into the testing side for for exploiting a large data set of information in order to give to the result also a statistical meaning. And this is one of the final goals also, to use this result for calibration of probabilistic models. So if you are interested in this activity for updated information on the progress of the experimental test, you can visit the project website that is updated with information about the ongoing research. Let me mention that an effort is ongoing within in general within the bridge engineering community, but also within specific professional association in order to promote further advances into these fields, particularly for life cycle design of deteriorating bridges and infrastructure systems under uncertainties, in order that this concept, criteria, and tools can be incorporated in risk-based design code and standards and be used in practice. And let me mention the International Association for Bridge Maintenance and Safety, extremely active into this area. This YAMAS association, as you know, also involve national groups. We have of course a group in Italy, there is a group in Japan, and they are all working into this along these research lines. I would like to mention also the International Association for Life Cycle Civil Engineering, and within the American Society of Civil Engineers, I would like to bring your attention on the Technical Council on Life Cycle Performance, Safety, Reliability, and Risk of Structural Systems that is making a strong effort in promoting all these topics with its 3 task groups that are working under the umbrella of the Technical Council. And one of the most relevant projects that is ongoing within this council now is aimed at addressing the effects of climate change on the life cycle performance of structures and infrastructure system. And this project is ongoing since 2 years now and is approaching the end, and final publication will be ready soon, reporting on the activity of this project. And in closing my presentation, on behalf of the International Association for Life Cycle Civil Engineering, I'm pleased to announce the 8th International Symposium on Life Cycle Civil Engineering, which will be held in Milano in next July under the auspices of Politecnico di Milano. And the response to the call for paper have been extremely successful. We received a contribution on a wide spectrum of advanced research topics and application in the field of life cycle of civil structure and infrastructure systems. And this contribution include over 50 mini symposium special session, and right now over 500 chatted full papers from 50 countries have been secured for the technical program. And this symposium will be held in the main campus of Politecnico di Milano. I really hope that you can join us for this event. And with this, I would like to close my presentation. Thank you for the attention, and I would like to thank you once again, Professor Waseda, and my thanks also to Japan Society of Civil Engineers. Thank you very much.
Thank you very much. Thank you very much for your valuable presentation. You gave us the research, interesting research covering the infrastructure systems, risk assessment, and the structural behavior of deteriorated concrete structures. So now we are starting to the short Q&A. So the audiences are open for discussion. If you have any questions and comment, please submit them through the Q&A box. So now we have received 2 questions. It's related to the non-destructive test. So in your presentation, Professor Biondini, you showed us inspection is important to evaluate the condition of structure. So how can we understand the structural performances of damaged RC bridges by non-destructive tests? So for example, which kind of non-destructive test method do you use to obtain the...
Yes, of course. If you refer to the experimental campaign I have shown, a large campaign of non-destructive tests have been developed and are currently under development, and they include sclerometric test, pachymeter test, ultrasonic test to characterize the mechanical properties of concrete, and also we made electrochemical test for corrosion characterization. And after the beams have been tested, we extracted a large number of samples for both concrete samples and also sample of reinforcing steel bars, pre-stressing and ordinary reinforcing steel, and we tested this in the lab. And all these the results of this preliminary non-destructive test have been elaborated to calibrate the structural models that we use to simulate the load test. Of course, the numerical simulation was aimed at one end to validate the models, but also to support a proper planning of the full-scale load test, because we have 29 beams to be tested, and in order to plan properly this test and cover a variety of scenarios, including different span ratio, but also taking into account a different load protocol and so on, we need to make a preliminary numerical investigation to predict which are the result of the experimental test.
Thank you for your answer. But I would like to know your simulation results is very corresponding to the experimental result. You showed some result beam test. So these beams, I think that these are pre-stressed concrete beams. So for these structures, it's important to evaluate the pre-stress, induced pre-stress, and if the rebar corroded, we have to consider the deterioration of rebar itself. So from your answer, I understand that you calculate the material deterioration after testing. So how do you estimate before test to evaluate the for example rebar corrosion or other important information from non-destructive test?
Yes, so you touched two very important aspects, and they were, of course, taken into account. For what concerns the level of pre-stressing, we had information from the design technical documentation, but using that information, we overestimated at the beginning the capacity of the beams, particularly more than the capacity, the preliminary part of the load displacement diagram approaching the load capacity. And in order to better calibrate the residual pre-stressing, we made a sensitivity analysis, and we found that the best value of residual pre-stressing was about 85% of the design value. This preliminary assessment of the residual pre-stressing was also confirmed by residual pre-stressing tests that were also performed on selected beams after the load test. And this result also indicated a loss of pre-stressing of about 15% with respect to what it was reported in the technical documentation. And of course, in the presentation, I have reported and shown only the final results that are the result obtained at the end of this quite long process. But of course, we have a series of intermediate results that show that the level of residual pre-stressing is really matter for a proper description of the structural response. Again, not for the actual load capacity that is almost independent on pre-stressing, but for the preliminary branch of the load displacement curve. The other point that you mentioned was corrosion. And for the moment, corrosion didn't play a strong role for the beam that we tested, because the central part of the beams were in a quite good condition, and the test that we performed were practically leading to a bending failure in the central part of the beams, either for the 3-point as well as for the 4-point, because still we are considering quite large span ratio, and the smaller span ratio will be considered in the near future. In that case, I believe the corrosion will play a much more important role, because the lateral parts of the pre-stressed beams are quite damaged by corrosion, because of course they are the most exposed part, related and affected by an incorrect water conveyance, and so exhibit a severe deterioration. So for the moment, I repeat, corrosion didn't play an important role into this preliminary test. We checked also the strengths after test, and they were in a very good condition in the central part of the beam, far away from the ends.
Thank you for your answer. It's very valuable for us. So now the time is limited, so we have received many questions, but I'm sorry I can't use these questions. So let's move on to the next presentation. So thank you very much,
Thank you.
Professor Biondini. So next speaker is Professor Mitsuyoshi Akiyama. Yes. So I'd like to introduce about Professor Akiyama briefly. He's a professor at Waseda University. His main research interests are in the life cycle performance assessment of civil engineering systems and multiple hazards. As scientific committee service activities, he has been serving as a managing editor of Structure and Infrastructure Engineering and an associate editor of JSCE Journal of Bridge Engineering. He also serves on the editorial board of Structural Safety and International Journal of Earthquake and Impact Engineering. He is also a member of the JSCE Technical Council on Life Cycle Performance, Safety, Reliability, and Risk of Structural System, in which Professor Biondini is the chair. So he is secretary of Executive Committee of IABMAS, Executive Committee member of IARCHE, and Vice Chair of Commission 6 Sustainability and Chair of Task Group 6.1 Disaster Waste Management in IABSE. Then today, he delivers a lecture entitled Toward Life Cycle Reliability, Risk, and Resilience-Based Design and Assessment of Bridges and Bridge Networks and Multiple Hazards. So, Professor Akiyama, please share your slide and start your presentation.
Okay. Thank you very much, Ueda-sensei, for your kind introduction. Good evening, ladies and gentlemen. It's my great pleasure to be here to make a presentation, which is toward life cycle reliability, risk, and resilience-based design and assessment of bridges and bridge networks and multiple hazards. So let me share my screen. Okay, so I hope now you can see my screen.
Sure.
So, okay, first of all, I would like to express my sincere gratitude to Concrete Committee, JSCE, for giving me this opportunity to present my research today. So first, I would like to introduce myself. I graduated from Tohoku University in Sendai City, Japan in 1995. So as you know, Kobe earthquake occurred in 1995. The severe damage caused by the Kobe earthquake made me think about becoming a researcher. Then I had conducted research on seismic issues in my bachelor, master, and PhD studies. So in my presentation, first I will give a short summary of research progress on seismic design methodology for bridges and lessons from recent large earthquakes in Japan. So strong ground motion is a still dominant hazard to structures in Japan. However, now we have to consider not only ground motion, but also other hazards such as tsunamis, landslide, flooding, and climate change. So I will talk about how multiple hazards should be considered. And I also explain the deterioration of concrete structures in addition to natural disasters. So in Japan, since Kobe earthquake, there have been so many large earthquakes with the magnitude of larger than 6.5. So structures and infrastructures in Japan have been damaged due to these earthquakes. The investigation of these negative consequences gave rise to serious discussion about seismic design philosophy and to extensive research activities on the retrofit of as-built structures. So the seismic design methodology for new bridges has been also improved. So this picture shows RC columns designed in 1970s. So the column failed in shear. So based on the experience of seismic damage to structures and research progress on shear and ductility designs of RC components, so we can see a big research progress and upgrade of seismic design specification has improved the seismic capacities associated with the horizontal load and horizontal displacement. So as a result, failure probability of bridges subjected to ground motion has been significantly reduced. So since post-earthquake restoration of damaged piers is challenging, time-consuming, and it causes traffic disruptions. So for new structures, capacity design methodology has been introduced. Also, high strength and high performance materials have been investigated. So even for existing structures, seismic resilience after moderate to essentially strong earthquakes must be taken into consideration in the retrofit of structures. So several technologies have been developed as shown in these pictures. So as I mentioned, failure probability of new and retrofitted bridges subjected to ground motion has been significantly reduced. So let's see what happened in the recent two large earthquakes, the 2011 Great East Japan earthquake and the 2016 Kumamoto earthquake. So these are pictures taken during the field investigation conducted after the 2011 Great East Japan earthquake. And these are pictures taken during the field investigation conducted after the 2016 Kumamoto earthquake. So some as-built bridges were severely damaged and collapsed. So Frio Overpass number 1, which crosses the Kyushu Expressway, collapsed, preventing the traffic passage. So rapid progress must be made in the seismic retrofit program. So the title of this webinar is Life Cycle Bridge, but during the field investigation conducted after the seismic event, some bridges didn't have any damages, but due to damage to embankment and other road structures, so functionality of road network deteriorated severely. So when estimating the consequences associated with the loss of traffic capacity, not only bridge failure, but also damage to other road structures need to be considered. So field investigations conducted after the 2011 Great East Japan earthquake and the 2016 Kumamoto earthquake confirmed that several bridges were severely damaged and collapsed, not only due to ground motion, but also due to the subsequent tsunami, landslide, or fault displacement. So these pictures were taken before and after 2011 Great East Japan earthquake. So although the bridge pier was retrofitted to increase the seismic performance using reinforced concrete jacketing, so you could see the difference of concrete color. So this is a reinforced concrete jacketing. So this seismic retrofit could prevent the damage to bridges due to ground motion. However, this couldn't prevent the washout of superstructure. So these are photographs of Aso Bridge with the span of approximately 130 meters and taken before and after 2016 Kumamoto earthquake. So the Aso Bridge was also retrofitted by seismic dampers here. So however, the Aso Bridge was completely destroyed due to the huge landslide caused by the 2016 Kumamoto earthquake. In addition, field investigation conducted after the 2011 Great East Japan earthquake confirmed that some of RC structures and steel bearings were severely deteriorated due to chloride-induced corrosion. Some structures are located near coastline and in Tohoku region, affected by the 2011 Great East Japan earthquake. In this region, during the winter, there are so many de-icing salt. So when evaluating the seismic performance, effect of deterioration on the behavior of bridges under strong excitation should be taken into consideration. Okay, so here is a background summary. As observed in past large earthquakes in Japan, field investigation confirmed that several bridges were severely damaged and collapsed, not only due to the earthquake, but also to the subsequent tsunami, landslide, or fault displacement. So in addition, material deterioration might cause further seismic damage to bridges. So the works at Waseda University to build a safer, more resilient, and more sustainable bridges and bridge networks and multiple hazards are introduced today. Okay. Also, the structural safety in design had been traditionally quantified by comparing the structural capacity with the load effect. So the uncertainties were implicitly considered when comparing the capacity with the demand. So evolution of structural design methodology from allowable design method to load resistance factor design method has revealed the importance of uncertainty consideration in balancing economical and safety aspect of structures. So however, this approach is not able to account for the consequences incurred from bridge failure. So because of large uncertainties associated with the prediction of future earthquakes, so we have to consider what happens if demand is larger than capacity. So a risk-based decision-making approach, today Fabio talked about this, needed to be developed. So in addition, the consequences associated with the sustainability and resilience has been considered. So finally, reliability, risk, resilience, and sustainability must be quantified in a life cycle context. So classical allowable stress and reliability were evaluated at the cross-section, component, and structure level. So a framework for quantifying the functionality loss, time to recover, and environmental impact of road networks involving bridges and other road structures, such as tunnels and embankments, need to be developed. So as I mentioned, field investigation conducted after the 2011 Great East Japan earthquake and the 2016 Kumamoto earthquake. So several bridges were collapsed due to the ground motion and the subsequent tsunami or landslide. So also several corroded bridges were damaged during these large earthquakes. So the design methodology of bridges must shift toward a more comprehensive approach of addressing multiple hazards to ensure adequate performance under different loading scenarios. So this is an illustrative road network under seismic and tsunami hazard. So they can cause bridge failure. So bridge failure causes severe consequences, quantified in terms of several measures, such as monetary loss, human fatalities, and environmental damage. So because the transportation network plays a crucial role in the evacuation of affected people and the transportation of emergency goods and materials. So the functionality of the network must be recovered as soon as possible after a disaster. So what is the key to enhance the resilience? Okay, so one of the most troublesome obstacles is disaster waste. So we should know seismic and tsunami disasters have always caused a lot of disaster waste. So this is the point: when structures collapse, they become disaster waste. So disaster waste really affected the overall recovery processes in the affected region. Also, a life cycle approach is needed in the reliability and risk assessment and quantification of resilience, because environmental and time variant stressors can reduce the structural performance and associated network functionality. So a proper modeling of the structural system over its entire life cycle by taking into account the effect of deterioration process and time variant loadings is needed. So when evaluating time variant loadings, effect of climate change should be considered. So as Professor Biondini mentioned, now in JSCE and in IABSE, there are some technical committees to discuss effect of climate change on the structural safety. So global warming will change the location of coastlines and increase the threat of tsunamis as a result of sea level rise. So intensified tsunami will be able to damage more bridges and cause larger disaster waste. So in addition, global warming will accelerate aging of infrastructure. So with the important three indicators, reliability, risk, and resilience in a life cycle perspective, and key technologies such as machine learning, numerical simulation, spatial modeling, and experiment to understand the real phenomena. So my research team at Waseda University is working on the following missions. Mission 1 is resilience of a road network and multiple hazards. We are studying about how to increase reliability, minimize risk, and enhance resilience of infrastructure subjected to earthquake and tsunami. Especially now, we are focusing on anticipated Nankai trough. So to investigate effect of climate change on the reliability and the risk of infrastructure, tsunami hazard considering sea level rise is developing. In addition to studies investigating the risk and resilience through quantitative approaches and application to case studies to bridge structures, research on the contribution to risk reduction and resiliency coming from structural control is conducted also in my team. So considering the impact of future climate change on the ocean, a method to estimate the tsunami hazard concerning sea level rise is needed to precisely predict tsunami disasters. So tsunami hazard is estimated by conducting tsunami propagation simulations given a sea level rise, while considering the uncertainties associated with the fault movement. So I'm working with Professor Koshimura. He's a specialist of tsunami and tsunami simulation. So with the big help from Professor Koshimura, we are conducting this simulation. Also, probability of a bridge collapse due to the resulting impulsive pressures of breaking waves and hydrodynamic pressures associated with water velocity is evaluated. So intensified tsunami due to climate change, in addition to strong ground motion, damages many bridges and cause a lot of disaster waste. So it is very important before the occurrence of the anticipated Nankai trough earthquake to establish the procedure of how the estimated debris generated by the disaster will be managed, considering deterioration of road network functionality. So we need to select a site for the disposal of disaster waste and increase the capacity for the disposal of disaster waste. Of course, we have to have a strategy to balance the necessary cost with the time required to dispose of the disaster waste. This is one of optimization problems. So seismic retrofit is still important to reduce the risk and enhance the resilience. So quantification of the risk and resilience associated with the damage to each bridge can help in prioritizing retrofit activities for bridges in a network. Also, we are trying to develop a damage-free bridge using a low-cost friction pendulum, fabricated by a three-dimensional printer, which can be easily applied to a developing country with an earthquake-prone region. So we are developing this new type of bridges with Professor Honda at the University of Tokyo. So damage-free is, I believe, a perfect solution for ensuring the seismic reliability and resilience. However, for giant tsunami, many bridges, even retrofitted bridges observed during the field investigation after 2011 Great East Japan earthquake. So many bridges would be washed away. So the accelerated bridge construction, ABC concept, should be applied to temporary bridges to save on-site construction, time, and help roads reopen immediately after the event. So now my team is developing a temporary bridge using precast reinforced concrete blocks with the connections composed of steel and concrete shear keys. The picture shows steel shear key and carbon fiber reinforced polymer sheet or a coupler of longitudinal rivers. Okay, so from now on, let me introduce mission 2, which is to advance the life cycle maintenance of deteriorated concrete structures. So we are studying life cycle performance of deteriorating RC structures using experimental evidence, probabilistic analysis, and finite element method. Also, we are developing a system to evaluate the structural performance of aging reinforced concrete structures automatically through integration of machine learning, numerical simulation, reliability analysis, and updating theory. So when concrete structures are located near coastline, their structural performance deteriorate due to the chloride attack. So this figure shows the relationship between performance and time after structural construction. So presented by Professor Dan Frankopol at Lehigh University in his paper, published in Structure and Infrastructure Engineering in 2011. So to understand the performance profile, many concrete engineers, including myself, conducted many experimental works. So from the past research in the literature, we clearly understand basic procedure of steel corrosion due to chloride attack. So when chloride content at the river is larger than threshold at the river, steel corrosion begins. The expansion of corrosion product caused the cracking and spalling of concrete. So this picture shows severe corrosion cracks on bridge pier, right? And we can see cover concrete spalling and on the concrete slabs. So however, still we are not sure how long can we use this bridge, or how much does the bridge performance deteriorate? These are very simple questions, but it's quite difficult to respond to these questions. So I will present one illustrative example to estimate the structural capacity of aging concrete structures. So corrosion-induced crack width can provide effective information on the deterioration level of corroded RC structures. So however, uncertainty associated with the relationship between corrosion-induced crack width and steel corrosion in RC structures is quite large. So the challenge is how the visual inspection result of corrosion crack width can be used to evaluate the structural resistance. So our target is just based on the corrosion crack width. We want to estimate the degree of steel corrosion, and using a numerical simulation, we want to evaluate the structural resistance. However, it's quite challenging because of many kinds of and large uncertainties. So this picture illustrates the structural performance assessment of aging RC members based on observational corrosion crack width, so using machine learning. So this framework included experimental study to understand the spatial phenomena on steel corrosion and associated corrosion cracks, so stochastic field to generate artificial distribution of steel corrosion, so development of a numerical database on relationship between steel corrosion and corrosion crack, machine learning, and finally probabilistic prediction of structural capacity. So the problem is very simple, right? We want to estimate flexural capacity of aging, not only flexural capacity, but structural capacity of aging concrete structures, only using corrosion crack width. However, we need these complicated steps. So I want to introduce some experimental results conducted at Waseda University. Waseda University has a large X-ray system to visualize the rebars in the RC beams. So you can see this is the X-ray image, and this one is longitudinal rebar, and this is star laps. And this is the corrosion cracks on the bottom surface of RC beam taken by digital camera. So X-ray help to understand how steel corrosion is spatial, not only in the cross-section, but also in the longitudinal direction. So corrosion crack width becomes wider with the steel corrosion. But even if, for example, the observed corrosion crack width is 0.5 millimeter, so corresponding steel weight loss are really variable. So to represent this random phenomena, we applied the stochastic field concept to corroded RC beams. So left figure shows the effect of longitudinal correlation of steel corrosion on the simulated steel corrosion distribution using multivariate spectral representation method. When the steel corrosion of a river has a low degree of longitudinal correlation, so the distribution seems more scattered, random along the river. So right figure shows how the transverse correlation affects the simulated distribution of 3 longitudinal rivers. So low transverse correlation means those distributions are more scattered among the rivers in the transverse direction. In contrast, high transverse correlation means the steel corrosion distributions are more correlated among the rivers. So it may be possible for 3 rivers to have a high steel corrosion, like this point, at a specific location simultaneously. So it was very tough for my team fully to understand a multivariate spectral representation method. So with super big help from my colleague at Lehigh University, Dr. Boccini and Dr. Basileos, so we finally generated artificial steel corrosion distribution, considering both longitudinal and transverse correlations. So the point is using stochastic field. Without experimental result, we can generate possible aging RC beams. And based on the comparison between experimental and computational result, finite element models are validated. So via random field and FE analysis, artificial samples composed of the corrosion-induced crack width and steel corrosion distributions over the RC beams are generated. So machine learning models are developed using a numerical database to estimate the steel weight loss distribution from the observational corrosion-induced crack distribution. So there are many machine learning models, but we have to use models which can consider spatial correlation of steel corrosion. This slide shows a conventional long-term memory LSTM model. So once we get the distribution of corrosion crack width from concrete members, trained machine learning model can predict the distribution of steel corrosion. Then load and deflection relation is provided by finite element model. Since there are model errors associated with the machine learning, so we have to use many possible distributions of steel corrosion in Monte Carlo simulation. So repeating the finite element analysis with the estimated steel corrosion distributions, so we can have a probability density function of structural resistance. So this is the case study using 2 experimental specimens. So crack width of case B specimen is larger than that of case A specimen. This is an experimental result and crack widths observed on the surface of this RC beam. So using the proposed procedure, including machine learning, numerical simulation, so we can obtain the probabilistic density function of structural capacity. So as I mentioned, we consider many kinds of uncertainties. Final result is probabilistic density function of flexural capacity. And after estimating the probabilistic density function, we conducted the loading test, and the loading test result is very close to mean value. However, it should be noted that loading test result cannot always provide a yield load that is close to the mean value. Awesome. Okay. Let me conclude my presentation. So based on the lessons from the damage to infrastructure caused by the past earthquake and tsunami in Japan, so I introduced some works in my team to build a safer, more resilient, and more sustainable infrastructure systems. So of course, we have not yet reached our goal. We would like to progress our research with both computational and experimental approaches while flexibly incorporating new technologies. So before closing my presentation, I want to say the studies presented here today are supported by several JSPS Kakenhi, and also I would like to thank my colleagues, Professor Frangopol, Professor Koshimura, Professor Honda, and my past PhD student, and my current PhD candidate. Thank you very much.
Thank you, Professor Akiyama, for your nice presentation. So, yes, so now, unfortunately, the time has passed the scheduled times since I had to estimate the time. So, let me move on to the panel discussion without Q&A for Professor Akiyama. And so now we continue to welcome Professor Biondini and Professor Akiyama as a panelist. I would like to moderate this panel discussion as well. So I prepared 3 topics for the discussion today, but time is limited, so I only asked the point topic 2 and 3. I'd like to ask to Professor Biondini and Professor Akiyama. So the second topics is validity and reliability of life cycle models. Yes, whatever from the presentation from Professor Biondini and Akiyama, they show the simulation result. But whatever we simulate, we need to assume some phenomena or behaviors. So that is the results of simulation depend on those modelings. So in order to confirm the validity or to show the reliability of life cycle models, how much should we or how much could we require simulation results precisely and accurately? Or how could we understand the result and use for practical application? So I'd like Professor Biondini to give us some comment concerning these topics. What do you think about it, Professor Biondini, firstly?
So thank you, Professor Waseda, for pointing out this aspect and posing these questions. As I presented in my talk, in my opinion, we can consider nowadays life cycle models, at least for structural assessment, quite well established. What is still absolutely open is the validation of these methods, and So particularly for practical application, it is very important to refer to existing databases. Or when this is not possible, it is necessary to gather information from inspection and non-destructive testing and diagnostics. Of course, this may be costly, but it is necessary at this stage because our knowledge about the different aspects of life cycle models is still quite limited. For example, one aspect that we still need to investigate is the effect of damage on the spread of uncertainties over time, because we are typically modeling several random variables such as material strengths, for example, or loads, with well-established probability density function, but this is for undamaged structures. As damage arises, the uncertainties will change in the intensity and in nature, and so we have this probability descriptor such as mean and standard deviation that evolve in time, but also the type of the distribution. And it is not infrequent that for some performance indicators in time, we can move from, for example, unimodal to bimodal distribution. So we really need information from existing structures to better calibrate this model. This is absolutely open. And another aspect that is not, in my opinion, still investigated in depth in literature is the effect of damage on the time variant redistribution effects in structures, in statically indeterminate structures, because damage also for example, constant dead loads may lead to have a significant internal redistribution of stresses. And so this means that the critical region in structure may change in time because of aging and deterioration. This was shown also by Professor Akiyama, for example. One important aspect is the variability, spatial variability of damage. In that case was corrosion, but also other damage mechanism may be characterized by strong spatial variability. And this is another aspect that we need to incorporate into life cycle models. And of course, the next steps should bring these models more extensively in practical application. And I believe that nowadays, either on the research point of view, we have well advanced models, but also in practice, practitioners are starting to use these cycle models more and more. And so we need an effort to make these models more reliable. Another aspect, if I can mention this in addition to these comments, is related to the level of complexity in the life cycle models. So we need to make this model as simple as possible, but we cannot neglect complexities when they are present in the problem. I make an example. We typically use the Fick diffusion equation to model chloride ingress using the one-dimensional solution, the one-dimensional form of Fick diffusion. And this is appropriate in many cases, but sometimes when the diffusion process is governed by 2D or 3D gradients of concentration, it is necessary to use more complex models. And this is depending on the type of structural members affected by diffusion, the type of cross-section, for example, is very different if you have a solid rectangular cross-section, for example, or a hollow core cross-section. You have different exposure for the reinforcing steel bars. For example, for bars that are far away from the corners, perhaps a 1D solution is appropriate and sufficiently accurate, but for bars in the corners, it is not. So we need to start to consider also these aspects, because when we make prediction on long time intervals, these complexities may play a role, and it is important to incorporate into the assessment.
Thank you very much for your comment. So what do you think about it, Professor Akiyama?
Yes, so now Fabio explained them very well, and it could be enough, but I will add something. So I presented the probabilistic density function associated with flexural capacity of aging concrete girders based on observational corrosion crack width. So in that case study, observational information could contribute to reducing uncertainty. But now can I share the screen? Yes. But as shown in this probabilistic density function of flexural capacity, so we can see very large variability, right? Like flexural capacity range from 55 to 120 kilonewton. Even in KSA, KSA means a specimen with a smaller corrosion crack width. So additional information can make the standard deviation smaller. So for example, if we have several observational information on steel corrosion, like every 2 years, so I mean, if there are multiple observational information, this can reduce the standard deviation. So now today, Fabio introduced YABMAS. YABMAS is International Association for Bridge Maintenance and Safety. So now YABMAS has like a technical committee of bridge load testing. The chair is Eva, I couldn't remember the last name, but anyhow, she is working at Delft University. So as you know, bridge load testing is a field testing technique that can be used to obtain more information about the performance of bridges. So the bridge load testing also contribute to understanding the bridge performance and reducing the uncertainty. Also, the point to consider is that, so finally, we cannot remove all uncertainties. So the decision makers have to make a decision under uncertainty. So this means we also have to study more about how to determine the threshold, such as failure probability. And also in life cycle analysis of concrete structures, we have to take into account many kinds of uncertainties. So currently, uncertainties associated with hazard assessment, such as earthquake and tsunami in Japan, we should consider these two big hazards. So, but these hazard assessment include very large uncertainties. So because the reliability of a structure depends on the dominant uncertainties. So for example, errors, uncertainty associated with the material strengths are not a big problem when estimating seismic reliability. So however, the uncertainty in the numerical simulation of deteriorated reinforced concrete members are still very large than those of non-corroded RC members. So in that case, we should improve the numerical model to reduce such uncertainties. So the model, of course, need to be verified through comparison with the experimental result. But I would like to say that it's meaningless to discuss the accuracy of individual models used in life cycle analysis. But it is important to evaluate what uncertainties affect the life cycle reliability of concrete structures. And it is important to develop and improve the models if their corresponding uncertainties affect the structural reliability significantly. It's my comment.
Thank you very much. So let's move on to the final topics of the perspective of the life cycle bridge engineering. I'd like to know I'd like the professor to comment the perspective of these engineering. So, Professor Biondini?
Yeah, sure. I believe that in the near future, one of the main goals in developing life cycle bridge engineering is to try to fill the gap between theory and practice, and to bring theoretical concept into professional activity. And for this reason, what we need is to give a strong impulse in the updating of standards and design codes. This is extremely important, and the concept to be incorporated include several of the aspects that were mentioned also by Mitsuyoshi in his presentation, including sustainability, resilience, how to take into account for multi-hazard exposure. And also important is climate change. Climate change may have a strong role in life cycle assessment because it is leading not only to increase the intensity, the magnitude, and the frequency of extreme events, but it's also because of the changing in the environmental condition is leading to accelerate the rate of deterioration of materials and the damage processes such as corrosion. And this has to be incorporated into design practice and has to be taken into account also in design code. As I mentioned, there is a project ongoing within the American Society of Civil Engineers that is trying to foster this kind of developments, and with a strong attention for possible implementation into design codes of these aspects related to climate change. Another point I would like to mention is cost. When we say that we need to gather additional data, this is not only about the structural behavior of bridges, but also about the cost estimation and cost and calibration of cost models. This is extremely important if we want to use life cycle concept to support the decision-making process of public authorities. And what is missed is particularly information about indirect cost, because indirect costs can be extremely large. Sometimes they exceed by far the direct cost associated with bridge repair and rehabilitation. Indirect cost, I mean the cost associated, for example, with the loss of functionality at the network level. Just to make an example, fortunately, you know, we had this big failure event in Italy, in Genoa, with the collapse of the Politecnico bridge, and it was estimated that the indirect cost associated with the loss of functionality of the system, because this bridge was connecting two important parts of the region, and Genoa is also is one of the most important ports in Europe, involved a loss of over 400 million. And this exceed is more than double the cost of reconstruction of the new San Giorgio bridge that costed about 200 million. And this is just to give an idea of how important can be indirect cost, and So if we want to support the decision-making process of public authorities, we have to be able to account for these also cost items very reliably and accurately.
Thank you very much. So how about Professor Akiyama?
Yes, again, so Professor Biondini already explained very well about the future challenges. But I will add some point. Of course, I also agree we have to bridge between research and practical field. So now there are many good journal papers, but still it may take more time to apply these research outcomes to the practical field in the life cycle engineering. Also, rather than discussing the safety of individual bridges, I believe the scope of bridge engineering will include assessing the effect of damage or failure of individual bridges on the system and networks in which they are involved. It's very close. Professor Biondini mentioned we have to consider direct and indirect cost. So considering estimating indirect cost, this is really related to system evaluation. So I believe in the future, bridge engineers need to consider more systems and bridge networks. So traditionally, bridge engineers have been designing cross sections, members, and structures. But in the future, bridge engineers need to also have a viewpoint of designing bridge networks. So in this case, yes, as I mentioned, not only reliability, but also risk and resilience will become more important performance indicators. And in addition to natural disasters, such as earthquake, tsunami, flood, and landslide, yeah, the effects of deterioration, and in the long term, the effect of climate change will be incorporated as a hazard. So as Professor Biondini mentioned, he was the chair of a special project, and this project report will be published soon. So I hope many of my colleagues will see this report and to learn so how we have to consider effect of climate change on the bridge safety. Thank you.
Thank you for your comment. So thank you for the virtual discussion. Now, I think it was very impressive us, and the knowledge and ideas given today must be valuable and push forward the study on the life cycle bridge engineering. It was also valuable to enhance our understanding relevant to such kind of research field. So let me close today's webinar. I appreciate Professor Biondini and Professor Akiyama and audiences. We received valuable presentation and had a fruitful discussion through the webinar. I again deeply appreciate all of you. Then we are going to have next webinar in September or October this year, but it hasn't decided the detail yet. The topics would be about concrete materials, maybe relating to the durability of concrete. Anyway, we will announce to all of you when the detailed information will be fixed. So I look forward to seeing you at next webinar again. Thank you very much for joining today's webinar. Thank you very much, Professor Biondini, Professor Akiyama, and audience again. Thank you very much.
Thank you. Thank you. Goodbye.
Fabio, thank you very much.
Thank you. Thank you, Akiyama. Bye.
Bye.